Modern combat aircraft operate at the edge of material limits and human endurance. Every flight generates vast technical data from engines, avionics, hydraulics, structures, and weapons interfaces. For decades, maintenance relied on scheduled inspections, experience, and post-failure analysis. Artificial intelligence changes this foundation by converting raw data into predictive awareness. Sensors embedded across the aircraft stream information during flight and on the ground. AI models process vibration, heat stress, fuel flow, and control surface response. Patterns emerge before faults become visible. Maintenance shifts from reactive repair to condition-based action. AI-driven diagnostics identify microfractures, wiring degradation, and thermal fatigue. That human inspection cannot detect. Early machine learning models compare live aircraft behavior against fleet-wide baselines. Deviations trigger targeted maintenance actions. This reduces unnecessary part replacement while preventing catastrophic failure. Aircraft availability increases because maintenance windows become precise. Readiness improves because fewer jets sit idle awaiting inspection. Logistics chains adapt because parts demand becomes predictable rather than reactive. Engine health monitoring demonstrates this shift clearly. Turbine blades experience extreme heat and rotational stress. Traditional inspection schedules assume average wear. AI tracks individual engine behavior in real time. It predicts remaining life based on actual usage rather than calendar hours. Maintenance crews replace components exactly when required. Engine failures in flight decrease. Training sorties proceed without interruption. Combat commanders gain confidence in sustained operations. Structural integrity benefits from the same approach. High-G maneuvers, carrier landings, and rough field operations impose unique stress signatures. AI models learn how each airframe ages. Fatigue hotspots receive focused attention. Structural failures become rare events rather than surprises. Aircraft service life extends without compromising safety. Fleet replacement timelines stabilize. Supply and logistics undergo parallel transformation. AI forecasts part consumption across entire fleets. Warehouses stock what'll be needed rather than what might be needed. Transport delays decrease. Deployed units maintain higher readiness with smaller logistical footprints. Maintenance crews spend less time waiting and more time executing precise tasks. Human expertise remains central. AI does not replace technicians. It augments them. Maintainers receive clear, actionable insights instead of raw data. Training evolves toward system understanding rather than repetitive inspection routines. Errors decrease. Morale improves. Experience compounds faster because feedback loops tighten. Operational impact reaches a strategic level. Higher readiness rates translate directly into deterrence. Aircraft launch when required without hesitation. Adversaries face forces that sustain tempo without degradation. AI-driven maintenance becomes a silent force multiplier. Combat power persists not through more aircraft, but through smarter systems. This transformation remains largely unseen by the public. No afterburners or missile launches mark its presence. Yet modern air power increasingly depends on algorithms working quietly between flights. Aircraft that appear unchanged externally now carry an invisible intelligence that preserves their readiness. Air superiority no longer rests solely on performance in the sky. It depends on intelligence embedded in maintenance bays and data centers.